So guys, just before the break, we just finished our first numerical example, and it was about checking a beam for shear. And I do have, or I'm going to teach you right now on how to design a beam for shear. One more time, what you have seen in the last 10 minutes is to check a beam in shear. Now you will learn how to design a beam in shear. Now, guys, I know some of you already said, okay, you know what? Same as we said, if I have a force or a shear force, and this shear force is, let's say, 500, I want to resist, and concrete can do only 100, then why don't you take the 400 and simply find the spacing between the stirrup? Okay? So, but the thing is, this VF, the force that I'm trying to resist, is not constant. Is it changing along the beam center line? So please look at my screen. Look at my screen, and if I ask you on the screen, is it simply supported or a cantilever or continuous beam? I think by now almost 100% of the students can answer this. Is it simply supported? Actually, the answer is on the
Yes.
slide.
No,
It
no,
is.
I knew it. I knew it before I read that. It's simply supported.
I know, Matt, you're okay, you're totally fine. So so it is simply supported, and I guess also about at least 50% know that the sheared force diagram, if you have a uniform load on a simply supported beam, then the shear force diagram will look like the blue line. Do you see this blue line? This is the shear force diagram. Very simple. It's kind of two triangles. It goes from maximum at the face of the column on the left support here. Very simple. It is W multiplied by the clear span divided by 2 because this is the reaction. And on the other side, it is the same thing. However, here in this discussion, we're trying to design our beam. And let me ask you, did you ever learn the word envelope in my class? I said it a couple of times in several spots in my class. Did you hear the word envelope and what does it mean? Let's see, guys, if you're still remembering.
You mentioned that about in Safi, first of all.
So what is envelope? What is an envelope? What's the difference between an envelope and diagram? Can anybody answer this, guys?
The diagram will only identify how the beam behave in terms of um, uh, bending moment and the shear force. That's what only you can identify. But the envelope will tell you the whole thing: deflection, bending moment, and displacement.
Anybody else wants to add to what Jelly said or against what Jelly said? Guys, please, I need one more. Please, one more.
Bending the envelope is taking all the possible load combinations and putting them into one and then finding the maximum at all the points.
Nick, I like what you said, but I'm afraid. So what you said is correct, but I'm afraid it will be misunderstood. So when it comes to load combination, I'm not saying uh, uh, or actually you're right, like actually you're right, like the thing is envelope, it means maximum. It means the engineer or the designer is trying to find what is the worst case scenario that can happen to one section. Okay, so we've looked at the envelope for the bending moment, and now we will look at the envelope of the shear. But let me ask you, when we do the design, do we do the design based on diagrams or envelope? What do you think?
Envelope.
Guys, hopefully everybody agrees with Nicholas that when we do a design, whether for bending or for shear or any other thing, we design for envelope because envelope is the maximum, which means there is not a single time that the force, whether this force is a bending moment or axial force or a shear, will exceed what's come in the envelope. So guys, here is the time that we will, first time we look at shear envelope. We've never seen this before. So this is the first time in my class we will look at shear envelope. And the blue line is a diagram. It is only one scenario. So that will be the shear for one scenario. And guys, please be patient. You will see, I know it's a little bit different. So if you put uniform load on top of a beam, what happens is your diagram will simply maximum at the face of the support, 0 here. Please watch this. I'm going to point to the 0. So the 0 is here. You can see the blue comes to 0 at the mid span. So, but again, as I said, the blue is just a diagram, not an envelope. And you will understand how do we develop this red, because the red is an envelope shortly. Okay, so now if we switch to this beam, what do we call this beam?
Continuous beam.
It's a continuous beam, and you don't have to know how many spans. I'm just providing here an intermediate span. So there is a span on the left, and how many on the left we don't know, or how many on the right we don't know. But looks like the when it comes to the shear of the simply supported and the continuous, they look almost identical. The only difference is, I even put it here in red, that this number here is multiplied by 1.15. So we have the same reaction, but the reaction is increased by 15% because of the continuity. The continuity, it adds more reaction to the support. So we got here 15%. Other than that, looks like this diagram here, it is pretty much like this one here. And then finally, if we look at the cantilever, so this beam here, I'm sorry, this is not supposed to be like a hinge. Otherwise, it is unstable. This guy will fall to the ground. But think about this one as fixed. Okay, so this is called the cantilever. And for the cantilever, simply the shear force diagram will be at a triangle, 0 at the tip of the cantilever, a maximum at the fixing point. And you can see there is no over 2, huh? There is no over 2. It's W multiplied by the clear span. Now, I'll do my best to explain it, but if you don't understand, that's also fine. So this is how we do the envelope. So guys, what really causes the problem is the live load. So live load is transient, which means it can move. And this movement of the live load, it creates little problem, because simply when you move the live load, it simply changes the diagram. And that's why here, I'm gonna make your life easy. I'm not gonna ask you to try all the load combination configuration. Only think about 2. Number A, which is here, I'm putting my live load on full span. So the entire span is covered by live load. And what do we get? We get what you know. We get this one here with a maximum value at the support and 0 on this at the mid span. How about if I change my live load not to cover the entire span, but also only cover half of the span? It can happen, by the way. Live load, you cannot guarantee. It can cover the full span, and it can cover half of the span, or maybe portion of the span. Okay, so let's please look at this example here. And if you do the math, you will see this is the shear force diagram if the live load is covering only the left half of the span. Okay. Now you can see, do you see any problem? I'm going to show you guys. If I take this point here and I drop a line, you will see on this load case here, on this load configuration, the shear force in the middle is 0. While if I simply make the live load covers the left span, you can see if I zoom in, the shear force is not 0. Look at this, please. So I'm going to mark it here so you can see this is the shear force, and it's not 0. And what does it mean? It means the blue line was not really my envelope, because you can see there is one case, if the live load covers only the left part of the span, on the center here, it's not 0, it is some value. Okay, guys, bottom line is, please, if you couldn't follow the discussion before, here is what you need to understand. The red diagram is your envelope, and it's not the blue. The blue is just only one diagram. The envelope is the red. How much? Very simple. Same value on the left, so W factor multiplied by N divided by 2, so no change, same value as the blue. How about in the middle? The middle is a little bit, it's not 0. The middle is 1.5. I'm going to zoom in, you guys can see. It is 1.5 times W live load, because dead load is innocent. Dead load has no business with this discussion. So really what causes at the middle span is the live load. So it is 1.5 because it's factored. So 1.5 multiplied by the live load multiplied by the span divided by 8. That's it. That's all I want you to know if you couldn't follow the previous discussion. There is one last thing here which I will simply go through in a minute. You can see at the support here, there is a little bit of something weird. Let me ask you what does it, or let me show you what does it mean. You can see here, I made my shear diagram dotted. So I kind of trimmed the shear diagram. I removed the bars of the shear diagram. And I will give you the reason why do we do that. Okay? Guys, any questions so far so I can tell you why do we do this thing? Are you guys following how we do the envelope?
Yeah, we're following.
Okay, now let me show you. Actually, this discussion doesn't apply for cantilever. So cantilever, no matter where you move your live load, it will come under your single blue diagram. And that's why if I zoom in here, you see the blue and the red, they are the same thing. It applies only for simply supported or continuous beam. A cantilever, all your diagram will fall here. So under the red, which means we're safe. Okay. Now here is why do we trim our diagram. Okay. So you can see my diagram, it's suppose, or what you have done before in the static classes, you draw the full triangle. So it goes here from 0, it goes all to the maximum. So today in concrete, that's what we do. We simply remove this bar. So this part is removed from the business. And by the way, that's easement. So you can see if I don't take this into consideration, I should design for this value here, because this will be the maximum shear. If you agree, How about if I remove this tip here? Guess what? This what happens. I should design only for this part here. Now, why this is happening? Why I'm removing this part? Okay. And by the way, some engineers will not do that, That's only for the theory. So I'm teaching you the right thing. Okay. So you can use this as easement to reduce your design shear force. Why this is happening? The answer is here. Please look at this. Guys, where is the first shear crack? The first shear crack will come from this point here, which has the maximum shear and will come roughly at 45 degrees angle. So the first shear crack will come from this point here. I'm going to point to from this point here, and will come at almost an angle 45 degrees. So guys, this zone here is very strong. You will never see any shear crack that goes this way, never. Okay. And so because of this reason, the code says, you know what? Let's estimate the shear force here at distance dV from the face of the column. So guys, this is a reduction for the design shear force. And instead of designing on this value, we simply go a distance from the face of the column. This distance is simply dV, because simply the angle is 45 degrees. 45 degrees. Okay, so in 45 degrees, the horizontal side is equal to the vertical side. So if the vertical is dV, the horizontal is also dV. And you can see if I estimate the shear force here at distance dV, for sure it will be less than the distance at the face of the column, which means I'm designing for less force. And this is an easement or reduction for your shear force. So guys, here is the idea. I know some of you probably by now think, oh my God, that this is so difficult. That's very complicated. It is not. All we have to do is you just draw the diagram that you know from first year. So WLN over 2, LN over 2, and in the middle is not 0. In the middle is this value. And then next is you simply mathematically you cut, and I will show you how to do that. Similarity of triangle. So we and simply the red continuous line becomes my shear envelope, and that's what I'm going to use in my design. I want to make sure that so you guys are following so far, because I'm going to build on that. I'm going to build on that.
Yeah, we're following.
Okay, so now let's go to the next part here. I want to give you the general idea of what's happening. Huh? So what's happening is now you can see my shear force is simply changing. Huh? So look at this, my beam here. So this diagram here is my envelope. So let me give you this option and tell me if I'm a good engineer or good designer or no. I I will take simply this value here. I'm going to mark it with dimension line. I will take my VR maximum, or sorry, my VF maximum after the reduction. And let's say this number, let's say it is 400 kilonewton. Okay? Now, guys, let's say concrete can take 100. Let's say concrete can take 100. So I'm asking you, what is the responsibility of the stirrup? How much?
300.
Excellent, 300. Now, if you take the 300 into the stirrup equation and find the spacing, remember here it's reversed. In the previous problem, when we do the check, the spacing is given and we're able to find VS, like the responsibility of the stirrup. In the design, it is reversed. So we know how much the steel can take and we know how much concrete can take. I'm sorry, we know how much the shear force and we know concrete can take, and the rest will supposed to be resisted by the stirrup. Okay, so we know that the stirrup is supposed to resist 300, and now I can find the spacing of the stirrup that can give me the 300. I'm asking you, let's say I found the spacing is 150 millimeter. Let me ask you, should I use this 150 and I apply all the stirrups for all the beam at the same spacing at 150 millimeter on center? What do you think?
No,
No.
And why no, sir? Like, why do you feel that's no?
because you only calculated for one section of that beam.
Which is the maximum. So I'm already making the maximum safe. Remember, look at where I placed the 400. It is at the maximum shear. And based on the remaining for the stirrups, I found 150. Okay? I'm asking you, should I take the 150 and I place it everywhere on the beam from between the columns?
No, it'd
Yes.
just be a waste of
You're gonna
material.
end up in a ductile failure if you replace it like that because you calculated it for max shear. That means it doesn't need it everywhere like at 150 millimeters.
Domenico, you said few words good and few words bad. So this has nothing to do with flexible or ductile or brittle. Okay? In my design, I will make sure that this is a ductile failure. But the thing is, do I really need, look at the diagram, watch the diagram. So diagram, the value here is 400, okay? And here is also 400 because that's flat horizontal. And from this point, it goes down, goes down, goes down, and it goes down, and it goes down, right? So you can see my shear force is simply depreciating as you go to the center of your beam. And it means, remember, I did the design at the maximum shear here, which is 400. But this 400, it will go down as you go to the center of the beam, which means what happens to this 150? What do you think?
You only have to put the 150 where the 400 is belong. Where the limit for where the 400 is.
So, Jelly, let me ask you, what if I ignore what you said and I kept it at 150 constant? What's the
And
problem with this?
you're gonna be over. You're gonna be putting a lot of stirrups because the shear force is reducing. Is reducing when you go down. It's reducing. So that means
Thank
if
you.
you keep
That's it.
going 150.
Yeah,
Okay, go ahead.
thank you so much. What you said is perfect. It's 100% correct. So Jelly said, if you keep with the same spacing, it means your shear capacity for the entire beam same 400. While the applied force here is so little, like the applied force here is so little, which means, okay, guys, I'm gonna show you something interesting also. Let me clean this a little bit. Okay, so I'm saying here, I'm gonna make another line. So this line here, it is simply the capacity of the beam. So the capacity of the beam in red, I made it and I designed it to be 400. And look at my graph. the capacity of the beam is still the same because I didn't change the spacing of my stirrup. So it will be the same at 400. While look at the VF. So this diagram is VF and this diagram is VR. So the VR is quite bigger than the VF when you go to the center of the beam. And that's why, as Jelly said, this will be not really best use of the material. We're wasting a lot of material. And that's why this will take us to how we design our beam. So how are we design our beam? Simply in region. Please look at my diagram here. We design the beam in regions. Okay? And so first of all, we look at can I get rid of all the stirrups? Maybe yes, maybe no. It depends on the code. So code, yes, ask you sometimes, no, I need some stirrup, and sometimes no. And then after this zone here, which maybe, I'm gonna maybe make it a square here. So maybe this zone here maybe doesn't need stirrup at all because concrete is good and it can do it on its own. I'll do that some coloring, So this zone here probably concrete is okay because the shear force is very little. So concrete can survive on its own, no need for stirrup. But as we go from the center, go to the support, what happens to the shear force? It increases. And because it increases, then maybe it will go above what concrete can handle. And we, at some point, we will start to need some stirrups. And that will take us into region number 2. Sorry, in this diagram here, I call this one region 0, and this one is region 1. By the way, those names are not important, like whether you call them region 1, 2, 3, or 0, 1, 2, 1, or A and B and C. Really, most important is what's happening in the region. What characterizes this region? So what characterizes the yellow region is, and there is no stirrup, it is concrete only. What characterizes the following region, I'm going to maybe give it a different color here, which is between this point to this point here. I'll give it a different color. So this region probably like in green, this region here, we will start to add some stirrup. But the question is, are we able to add any amount we like? Like, let's say I want to add 10M at 500 on center or 600 on center. Is that acceptable by the code? Or the code has a minimum stirrup that you must add? What do you think?
The code has a minimum.
If you're paying attention, we've said this already, the code has some requirement. And since we are adding a stirrup, what happened is in this green zone, we will add the minimum amount of stirrups, okay? But then this minimum plus concrete can provide only this much VR. So if you see how much is my VC in this zone, plus how much VS based on the minimum stirrup, what happened is it will give you a certain level of VR. Is that okay? Maybe yes, maybe this zone is able to go all the way to the end. Maybe sufficient, but maybe not. Maybe the minimum stirrup cannot do it. And that's why at some point we will have to stop region number 1. And in region number 2, for sure, we will add more than the minimum stirrup that can handle my VF maximum. Guys, the whole point of this discussion is to make economical design. Wherever I don't need stirrup, I'm not going to add stirrup. Whenever I need the minimum, which I cannot add less than the minimum, then I will use the minimum. And then if the minimum is not sufficient, then I will need to provide more than the minimum. Are you following?
Yes, sir.
Okay, so let's move on. And, I know some of you, maybe 50% of you guys, not clear of what Tahir is saying by now. But let me show you when we give you a numerical example. Let's see if this can help. Okay, so here is your first, and I decided, to be honest, that maybe that's not sufficient. So my decision is I was about to give you another example to read on your own. But what I will do is on Monday, there will be another example, and the assignment will be published on Monday, and it will be due to the following Monday. Okay?
That will be Tuesday next week.
Yeah, Tuesday. Why?
Yeah, because Monday we have our concrete contracts exam.
Oh, okay. Sorry. Whatever. But I mean, the exam is not connected to the assignment submission. But if you are asking for extra day, that's totally fine by me. Okay.
No, we have the switch classes on the beginning of next week.
No, but
Right.
what I'm saying, but oh, sorry. So I'm teaching you next week on Tuesday, not Monday, huh?
Yeah, because we switched it with contracts.
Perfect, perfect. So I'm going to teach you guys another example, similar to this one, but on a cantilever or any other example on Tuesday, and the assignment will be 1 week from Tuesday, so it will be the following Tuesday. Now, let's see how can we design a beam. So here is a beam, and you can see, hopefully you notice that, this beam or this problem is a design or check. Look at the cross section. Is it design or check?
Design.
Design. There is no stirrup inside. By now I don't know how many legs. I don't know what is the stirrup diameter. I don't know what's the spacing. So it is a design. I have to figure all of that. And now the beam here is given. The beam is center line to center line 6 meter, and then the column is 400. The load on the beam is 100 kilonewton for dead load and 60 for live load. Or some other information here when it comes to F prime C, F yield, and some other constant. Also, you need the reinforcing bar because this will help you to find your effective depth. We also give you here asking you to use 10M, which is, by the way, so you know that's the norm. The norm is using 10M for stirrups. For heavy beams, very heavy reinforced beam, we go to 15M, but the norm is 10M. Okay. And concrete cover, clear cover is 40. And let's go, let's see. So guys, number one, as usual, what you have to do is you need to find your D, which is effective depth. DH minus cover plus stirrup plus half bar. You'll get here 635. Now, from the effective depth, you will find the effective shear depth, which is the greater of two numbers, 90% of D or 72% of H. And then finally, you will take the maximum, and here the number was 571.5. However, in my calcs, I chose to be 170, 570, and I wrote the reason. Rounding is only to ease the calculation. Rounding, so this rounding here, it just eases the calculation, and you will see where I'll point out when it comes to this. So I just ignore 1.5 mils. 1.5 mil, very tiny.
Sorry,
Now,
Tahir. I have a quick question just for that part. We don't need to check our minimum B value to see if we have two layers first.
you know what? Like the beam here is quite wide. Like, look at the beam wide is 600 millimeter wide. And if you wish, but let's. So the beam design already has been finished. The beam flexure design has been finished. So somebody else did the check for the width. And I bet you go ahead and do it. You will see 600 is too wide. It can very, very comfortably can take the 4 bars 30M.
Okay.
Okay, so guys, please pay attention, and this is happening in the assignment so often. You guys are not paying attention that when we estimate the bending moment or the shear, we use clear span. Take a note, please. We use clear span. And look at the elevation here. The dimension is going to the center line, to the center line. The clear span, very simple. You take 400 of 6,000, you will end up with 5,600. Now, very quickly, we do the load combination. So we add 1.25 times dead load plus 1.5 live load. So here is my factor the load. And of course, you have to do LC1, which is 1.4 dead, and take the maximum. But I've done this already, and the maximum is 215. Okay, because 100 times 1.4 is 140, and 140 is less 215. So that's my factor the load. Now, once you know the factor the load, we multiply times the span divided by 2. And why is that? Guys, please don't tell me multiply by the span square over 8, because span square over 8, that is the moment. We're not designing for moment right now. I'm trying to find the maximum shear at the support, which is I multiply by the span divided by 2. So W factored over there multiplied by ln L divided by 2, and here is my shear force 602. Now, something I will do before I continue, which is trimming my diagram. So we know that whatever I estimate 602 is, is simply happening at the face of the column, right? 602. How about what's happening in the middle? What's happening in the middle here? We know from the previous discussion it's not 0. How much? Look at this. There's 1.5. Live load and live load only, huh? Live load only. Multiply by the span over 8, so you get 63, not 0. So that is this line here. This diagram here is half my the envelope. You can see I wrote it here clearly in red. This is half of the diagram because it's symmetric, huh? It is symmetric, so everything is symmetric around center line of the beam, not center line of the column, center line of the beam. So what you see on my screen is only half of the beam. And you can see this 2800. 2800 is 5.6 meter divided by 2. And everything I do here, I'm going to mirror, huh? So all my calculation, I don't have to repeat. It's just a mirror. Okay? You guys follow that? Are you following?
Yes.
Do you guys remember this discussion of those zones? Okay? You can see here, this is the center line of my beam. So I'm going to only do all my calcs for half of the beam, but then all my finding, I can simply mirror around the center line. I apply it on this side here. Watch this, please. So there is also on this side, there is the same green zone. Okay? Okay, let's move on. So guys, first thing you want to do, you want to check, make sure the concrete dimension of your beam, it works. So what you have to do is you simply go to the same equation, 0.25 times 0.65 times 25 times the width of the beam times the d sub v, and this will give you VR maximum. And remember, I'm sorry, I have to probably tell you something here, guys. Look at this, please. So I found already my 602 and I found my 63, and I said that this part here, it has to be removed. Not has to be honest. It doesn't have to be. Okay, that's easement, that's reduction. So a good designer or engineer will simply use this reduction. Otherwise, he or she will come up with more steer up that is than required. Okay. So how do I remove this part, guys? Pure math. I'm going to go through it, and you will see this happening several times in this problem. So guys, the dimension from the, remember the beam is here, that's the baseline, to this point 602. Now I said before, this we have to trim the diagram at distance dv. You can see the dv is over here. So this is 570, which is the d sub v. So I want to simply remove this part at distance d sub v. Mathematically, what you do is simply you estimate the distance from here to there, and there's no super signs. This number is how much? This number is 602 minus 63, okay, which is 539. So guys, I'm going to move it here. So this dimension here is 602 minus 63, which is here. So I did it here. That's 539. And then what you do next is you do similarity of triangles. Okay? Remember the dimension from here, from this point to this point, sorry. So the dimension from this point to this point is how much? It is 2800 minus 570. Okay? 570. And you can see I can do similarity of triangles. This triangle here and this triangle over there, and you can see the math is over there. Please take a look, huh? So I'm going to call it X. So this is X. This is X. This is called X because I don't know how much is my shear force. Okay, so X is X over 5 over 2800 minus 570 is equal to 539 over 2800. And what you do is you will find your x, and x is equal to 429 kilonewton. Remember, really the x is not a shear force, because remember, the shear force is always estimated from the datum. So the datum is your blue line, which means all you have to do is add again this distance here, which is 63. And then finally, you have to add 63 to your x. And then finally, you'll get 492. And what does it mean? It means, guys, look at my blue dimension. Look at my blue dimension, 492. This is my new shear force. So you can see how much did I save, huh? I supposed to design for 602, and after I did this reduction, I'm going to design for only 492 kilonewton. Are you guys following? I'm trimming
Yes.
my diagram at distance dv from the face of the column. I'm cutting my diagram at distance 570 mil from the face of the column. The discussion here is pure math. Please don't be distracted by the math. The idea is I want to find what is the shear at distance dv from the face of the column. Mathematically, it is 492. And remember, I did some saving. Instead of me designing for 602, I'm going to design only for 492. And you can see there is quite saving here. Now, going back to my check, you can see my VF is way below my VR maximum. Are we okay? We're okay. And I, guys, please pay attention to this. I make it bold and in red. Otherwise, what happens if this is not happening? What happens if I found my VF exceeds my VR maximum?
Change
what can I
some
do?
of the concrete. Change
Change
some.
the
Change
beam.
concrete dimensions, B and H, and
Yeah.
change concrete compressive strength. And remember, what do? We do before any calculation starts. So which means my dimension of my beam that I'm trying to start with is not good. I need to change, resize my beam. Here we go. So those dimensions here, they were not good. You have to change them or change F prime C. But please don't continue. If this condition failed, it means don't continue. It means you have to do something, change it. Otherwise, if you continue, by the way, nobody's going to stop you. You can continue. But what happens is you will find so much stirrup required, and this much stirrup will simply ensure that your beam will fail in a brittle way in shear. Okay? Please don't do that. So anyway, so here is how we proceed. We're talking here about zone number 0 or region number 0. Guys, please, in the exam, now, take a note. In the exam, in the assignment, please follow 100% what I'm saying right now. I don't care what you call this zone. Call it Tahir, anything. Call it anything. I don't care region 0. But really what I care is the description of zone number 0. No stirrups. It means concrete only. And why I can do that? Why can I, for zone number 1, why can I make it without any stirrups? Because the beam depth is 700, which is less than 750. And the code allows you to go without stirrup if you go less than 750 or 750. But if your beam is anywhere above 750, this is not happening because the code said no. If your beam is more than 750, you must add stirrups. Is that clear? So
Yes,
please,
sir.
number one, write the description of the zone. And why I said here no stirrups? Because of the beam depth. So if I go back and change this problem and I make it 800, the solution will change because zone number 0 or region number 0 cannot be without stirrup because the code says no, you cannot. Okay? Anyway, for this problem, I'll make it simple. I'm going to say here, you know what? Let's estimate our VC. And you can see there is no surprise. There are some stuff available for you like phi C and lambda and F prime C and the width of the beam. But there are a couple of things you have to find. DV, which you already found, 570 millimeter. And then the beta here is what we will cover next. So guys, beta, we have two code clause. One, it says if you have minimum reinforcement, then it is 0.8. And if you have no minimum reinforcement, you use this equation to 30 above 1000 plus dV. So that's how I got my beta. So if you have in any beam section or part of the beam that contains minimum stirrup, then I use 0.8. Anywhere I don't have any stirrups or less than the minimum, I use 0.15. I'm asking you in zone number 0, which one? In zone number 0, region number 0, no stirrup. So I'm asking you, which value for the beta should I use?
B.
0.15.
Exactly, and you can see it's over there. And I can tell you, it means, guys, zone number 1, where concrete works on its own, how much concrete can do? It can do only 166. Okay? And then now, which is pure mathematics, pure mathematics. Now, what you have to do is, okay, you can see 63 here. My VF is 63. Good or bad? Concrete can do it or not?
It's good.
Yeah, I can
Good,
do it.
And then next what? Let's say another point here. Okay, I'm climbing along. I'm climbing along the diagram. You can see my VF is keep increasing. Where zone number 0 can end? Where
166.
where the VF equals to 166, which is VC. So really what we have to do is we need to find mathematically where is X0. Mathematically, pure math, no concrete. So what we have to do is we know that the distance from here to there, we know from here to there, this is 166, okay? The question is where the force will be, or the VF will be 166, I'll tell you it's not very difficult. Please watch me, I'll show you how. First of all, please subtract, the 63, because it's trapezium, it's trapezium. So subtract 63, you will get 103. Now you have 103, and remember, similarity of triangles, So this triangle here, not the trapezium, triangle in green, is similar to this big triangle here. So all you have to do is just simply do the math, do the similarity of triangles, and find x0. I put here the math. I'm hoping the math is right. Okay? And remember, guys, please don't use 602, That's a mistake, because simply we're talking about triangles, which means it has to be from here down to here. Please don't include this 63. So what you have to do is, this number is 539. Why 539? Because simply it's 602 minus 63. And remember, we have two similar triangles. The mass is on the right side here. And finally, x0 is equal to 535. What I did is I simply rounded to 25 millimeters. So you cannot tell the people on site, this area is 535. Make it nice number, So 500, which means the 500 from the center line to this point here, we don't have to add any stirrup. Are you following so far?
Yes.
Yes.
Okay, guys, I know I have 2 minutes. So what I will do is I will do zone number 2, and then next class I will do zone number 2 one more time, or probably I will start from zone number 0 again. Okay, so zone number 2 here, or region number 1, which follows region number 0 going to the support. Now, again, I don't care whether you call it Tahir or Hassan or region 1 or A or B. I don't care. I care you tell me in this zone, concrete plus minimum stirrup. Okay? Now, what happened is, we know concrete in this zone. We already found it. If you remember, we already use here 0.18, which is beta if I use minimum stirrup, and we know in this zone concrete can do 200. So we know this part already. But the thing is, how much the minimum stirrup can do for me? And the question is, what is minimum stirrup? Okay? Guys, I think that's too fast, so I will just stop here. I don't want to keep, pushing so hard. We still have our class on Tuesday, so I will stop here at this point, guys. And by the way, it's very simple to understand. If you want to continue reading the lecture notes, you will see it's very entertaining. Okay, any question for now? Thank you, Domenico. Guys, any question for now? If you have no question, our class is finished, and I will see you guys on Tuesday. And I think I sent you already a meeting invitation for Tuesday. So there is no, I removed the Monday meeting and I moved it to Tuesday. And I think Wendy also is asking for another week, but I think she never confirmed it so far. I think she has like a guest speaker, and she wants to switch as well. So, but again, for now, it's just this coming Tuesday. Okay? Have a fantastic day.